CAD tutorials, computer-aided design, which basically means we practice designing some 3D models because we would have to print them later. And in the other two pictures on your top left and bottom right, we did some 3D printing and laser cutting, all to assemble our robot. But mainly what we focused on in week 1 was training models on Donkey Sim, which is it's a driving simulator. And using that, we were able to practice collecting data and training models without having our actual robot built yet. In week 2, we wired up and finished assembling our car. As you can see in the bottom 2 photos, it seems a lot more simple than it actually is because often parts were missing, parts were breaking. For example, that yellow piece over there, the anti-spark switch module, we had to resolder that again 3 times, each time in all different parts. And every time we'd have to take it off the robot, resolder it, and it was a really big pain. In the top left photo, we see Carlo and Advik. Carlo was working on setting up our Jetson Nano, which is like the brain of our robot essentially. It took about 2 days worth of downloading stuff. It took a really long time, and Advik was working on the OpenCV edge detection.
As for week 3, we spent time going around the track and collecting data using the camera, which then we fed into Donkey Kart to train a model using behavioral learning. This model would affect how the car reacts when images are inputted and would output steering and throttle. We also had to troubleshoot a bunch of different problems that we ran into, such as the Jetson not having any of the dependencies, as well as the camera moving too much so that the data would get skewed. And by week 4, we started learning about lane recognition and working on it using OpenCV, which using the camera to check white lines and yellow lines to be able to follow the line and keep going around the track at a nice speed. We also set up LiDAR and used PySlam to set up the LiDAR, using a graph to use ray tracing and graph points to be able to map the area around us. We also use RoboFlow, which can detect stuff through camera.
So now we'll go over a little bit of the process of how we did autonomous driving. So we started off by collecting training data by manually driving laps. We used that to train a CNN, a convolutional neural network. We trained it on GPU clusters because they're really fast, and we ran the model on the real car. So how the training data works is the camera collects images at 20 frames per second, and at each frame it also records the throttle value, essentially how fast the car is going, and the steering angle. A convolutional neural network is a type of deep learning model that works really well with analyzing visual data, and yeah. One problem we faced though, as Carlo already touched on, was we made the camera mount adjustable initially so that we could find the optimal angle, but this sort of backfired on us because even though we thought we screwed in the camera mount really tight, it was moving and it was messing up our
a
data.
little bit. I forgot to record so if you don't mind, so then you can pause and then.
Awesome.
Okay, now into lane detection. So how it works is that OpenCV had a template called line following, which allowed us to trace the yellow line on the track. So what we did is that we modified that, so then we could see the yellow line, see the white line, and have a midpoint in between it. So over here we're masking out the colors. So we're only filtering for white, we're only filtering for yellow, and what we're doing is we're splitting up the image in the camera into a column of pixels, and then we're seeing which column has the most white, which one has the most yellow, and that's what we're sending into the next function. And these are our HSV values for our yellow and white. So those were the colors that we use. Here's a demo of our lane following program that we use with water bottles. And this is, you can see on the track, so over here we have the car on the left, the car in the middle, the car on the right, and then you can see how the lines adjust. So the white line is for the white lane, the teal line is for yellow, and the green line is at midpoint. So you can see how whatever condition we had, the wheels would always turn to go in the middle of the lane.
Next comes the fun part, which is our LiDAR. Now, I don't know if many of you guys have heard about LiDAR, but basically what a 2D LiDAR does is it shoots out rays of light in all 360 degrees, and it measures the distance between the LiDAR and whatever object is in front of it. So in order to achieve our goal of mapping, we use LiDARs to determine the angle and distance of objects around us in order to create a map using ray tracing. Now, what is ray tracing? Ray tracing is basically generating a graph of the angles and distances that we get from our LiDAR. And what we did was we got our polar data, which is angles and distance, and we converted it to Cartesian points, x's and y's. Next slide, please. Now, one of our main issue was that our graph was only displaying 12 data points at a time. And 12 data points compared to 360 degrees is a slight issue, especially if we're creating a map that's dynamic and always moving and shifting to where we're driving. To fix this, we used matplotlib, which is a Python graphing library, in order to use functions like plt.pause, which adapt the graph every few seconds to whatever the newest status is. And this worked really well, along with us shifting from like a line graph to a scatter plot. It was like adapting really fast, and we made sure of this by like testing it out in different areas and like covering the LiDAR and stuff, and it ended up working really well.
Now for object detection, we use RoboFlow to feed images and train a model using thumbs up or thumbs down. The idea for this is for thumbs up to start the model going around and mapping, and thumbs down to stop the process. So we uploaded the data set, trained the model, and we're able to successfully put it onto the camera, which is the edge of the process detection.
Now we'll talk a little bit about the Now we'll talk a little bit about the challenges we faced here. So first, we faced version incompatibility while installing Donkey 5. So basically, we had to install Donkey 5 in order to use OpenCV. But when we did that, we needed a newer version of Python. And after we downloaded the newer version of Python, which took hours, it still wasn't working. Eventually, we rebuilt the environment, but we lost all our previous training data. So that was a pretty big setback. When we broke our camera mount, we had to reprint it. Obviously, it took 7 hours, and so we were out for the whole day. The OAKD light, which is our camera, it turned out its field of view was too narrow, which caused a lot of problems in our training. So after we adjusted that, the training was a lot better. And you saw Advic's demonstration of the lane tracking. It works, it's really cool, but when the sun is on the track, it sort of blurs the light, it sort of blurs the camera view, so the white and the yellow look really similar, and it's hard for the camera to capture. So not only did that affect our lane detection on the actual track, it made training our autonomous vehicle a lot more difficult. And yeah, Conda broke on our last day, which was really annoying.
As for our future goals is to fuse LiDAR and camera data to improve the detection of our mapping and obstacle avoidance for the car to be able to go around autonomously and map areas. And then we also want to expand the gesture recognition, so meaning we can do different gestures. So just other than thumbs up and thumbs down, we can either point right, point left, and control where the car goes without having to have a controller. We could also collect more data to improve our models as our autonomous models in our CNN. Or we could also move the camera back to adjust for the lines and maybe change our colors to adjust for the sun as well.
So obviously through our month here, we've learned so much. We did some lane detection, LiDAR mapping, object recognition, and behavioral cloning. We used real-world tools like OpenCV, RoboFlow. We used the Jetson Nano, Depth AI, and remote GPU cluster training. And we did that. It was really cool doing all of this and integrating it into one robot and seeing it work. Through this experience, we also learned how to debug hardware and software issues under time pressure. And we also learned how early design decisions, such as the camera mount and camera angle, would affect our performance so much. And I feel like one other thing we learned, besides the technical aspect of this, is just how important teamwork is. It sounds cliche, but we learned to communicate and troubleshoot both within our own team and across our own team. Because, I mean, each one of us is different. You know, everyone here offers like a unique skill set, but the one thing we share is we're all so passionate about this, so it was really a great experience.
As for our acknowledgements, we'd like to thank Dr. Jack Silverman, Mr. Mike Ching Lee, Daniel, and Madison, who all helped us and guided us, as well as our fellow classmates Renzo, Tejas, Team 4, which really helped us, and Jabron.